Good morning, everybody. Welcome to the concluding session of the conference. We have had our first speaker this morning is Serge Cohen of Université Sabatier in Toulouse. And Serge will tell us about the fractional fields parametrized by manifolds.
Thank you very much. I will also thank the scientific committee and the organization, especially Pierre and Gennady, for inviting me. Actually, due to my duty, I'm learning a lot nowadays, and it is a special treat to be here with you and to hear such wonderful talks. And also a very nice, friendly conversation. And so far, it is perfect. I hope the talk will be in line, but let's see. Obviously, there is a strange word in the talk. It's the title, sorry, manifolds. And I still remember the conference is on adventures in self-similarity. So the question is, what the hell you do with self-similarity when you have a field parameterized by a manifold? Let's say something which is very elementary. What I have in mind is something which is not flat, which is a manifold. And for every point, I will consider a random variable or a field, and this random variable will be R value, even if it is random. So if you think to this rough picture, you see that the problem with the definition, with the very definition of self-similarity is, what is the multiplication by C, for instance? C is positive usually, but here you are missing some point. So the question, in some sense, is how to define self-similarity for such a general object. But maybe you can say, well, that's a silly question. Maybe there is no self-similarity for field parameterized by manifold. The problem is, in some sense, you have, there should be a meaning, at least. What do I mean? The problem is how we use a fractional field, let's say, parameterized by its flat space. One very famous application of the fractional fields is to get what people playing video games call textures. So it is a way to generate textures, generic textures, and obviously you can think of these textures parameterized not only by a square, your screen, but also you can put it on a sphere, you can put it on every surface, and in video games you have textures. So the problem is we need some object, but because we are mathematicians, the question is also, well, there are many textures, but we want to have something canonical to have a texture. You want to know what is a Brownian motion to which you could relate diffusion, for instance, in another setting. So I was thinking on this question for quite a long time, trying to imagine what could be the canonical field related to self-similarity on manifold, and actually it is a sad story because I still don't know. There are many propositions, but I'm not pleased with all these propositions. So I came back to something which is at least clearly defined, which is a fractional Brownian field. So let's write something that is that appeared previously in other talks. You know it very well. Let's consider the fractional Brownian field, and let's try to generalize this when here you don't have a flat space, but something more general. So there are different definitions for the fractional Brownian field, but here I consider the increments. And here you see you have a norm to the power 2h, if you take h as the first exponent, but Robert took yesterday alpha. Sorry. So I just put the picture here, just to have a picture, just to have in mind what I mean by a texture. By the way, I mean the simulation is not as good as the one you gave. I know it's not exact simulation, but it is only a picture to have in mind what is our goal. Let's go back to what I want to say. The first part about existence of Lévy Brownian field. I didn't say what is a Lévy Brownian field yet, but the first part is a review of quite old and classical results, mainly due to harmonic analysis, where you can show that there exists a fractional Brownian field on spatial manifolds. Because the problem is, obviously, I don't know how to define self-similarity. It's quite easy to define fractional Brownian field, but the problem is now the fractional Brownian field do not exist on every manifold. So on one side, I don't know how to define, on the other side, I may not have the object. Tricky thing. So I want to start in the first part to say sometimes it works. But it was quite clear that at some point it doesn't work for all manifolds, even really elementary and very simple manifolds. We have also old results concerning this part, but a PhD student of mine, Univeristé, just found some other way to see that some manifolds that where we want textures, and it is very simple to have textures on it, but you don't have fractional Brownian field. So let's think about a generalization of fractional Brownian field when you take as index space not even a manifold. You take just a metric space. Here we don't need additional structure. And it is obvious how you do that. You start from the previous definition, you consider you have something Gaussian. It's easier, at least in this talk. You still keep the center assumption, and you keep the variance of the increments, and instead of the norm you have on your vector space, you take the distance. By the way, all I will say in the first part is actually borrowed from Istas, and a nice review he wrote some years ago. You will have the reference at the end of the talk. So, as I said, it's obvious that when you come back to the metric space, which is a vector space with a norm, you recover the previous definition. And I've written in the previous slide that I will talk on Lévy Brownian field. Lévy Brownian field means I take H equal to 1/2. It is the most simple case. If you think to the one-dimensional case where you take R, it is a Brownian motion. On the other side, yesterday, Robert taught us about a generalization of the Brownian motion in many dimensions. And the one he chose was the Brownian sheet, just as Hermine Birmé did. Here, we are considering another extension of the Brownian motion in many dimensions. What is the difference, roughly, between the Brownian sheet and this Lévy Brownian field? For the Brownian sheet, you need to have axes, so spatial straight line. Here, the problem, or the tool you have, is you have a nice isotropy here. And even if you don't need this in the definition, it is clear that the group of isometry of your metric space will be very important to study this kind of fields. The problem is, for many metric spaces, this isometry group is very poor and doesn't help very much. One slight problem, which is elementary, we can solve it, is the question of uniqueness. Obviously, if you come back to this definition, here you use only the increments. It means if you add something to all the random variables in the definition of your field, it doesn't change the definition, so you cannot open it. about the uniqueness in distribution. One way to solve this problem, which is the usual way for the flat space, is you choose a special point, you call it the origin, and then you assume the field is vanishing homogeneously at this point, and then it is very easy to see that you have the covariance, which looks like very much the fractional Brownian field in the flat space. You just change the norm in the distance, and you also consider the distance to the power 2h. And then you have uniqueness of the law. It is a very simple problem, and I think you already knew that. So the problem, what is the problem? Why, on some spaces, you don't have a fractional or a Lévy Brownian field? The problem is quite clear. If this field exists, for every point, set of finite points you take, for every scalar you have, you should have, because you have a variance matrix there, this quantity which is positive. So actually, if you talk to people who are not probabilists, you don't even need to speak of probability, just a property of the metric of the distance on your space. And I would like, just as Hermine did before me, recall Schoenberg theorem. The problem is how to know that you have the positive properties for all points and all scalars written in this definition. Actually, the problem can be translated because if you assume, in addition, that the scalar the sum of your scalar is vanishing, then if you come back to the covariance you take for the Brownian field, you see that you have as a first factor this factor, then you have something that depends only on J, and then you have this last part. So you have you have a sum of three terms. The first one is this one, but this one, because it depends only on I, you can put the sigma j outside, and because you assume that it is vanishing, then you don't care about this. So obviously, if the Brownian field exists on metric spaces, you know that you have the distance to the power 2h enjoys such a property, and it is classically called a negative type property for functions. And we have a Schoenberg theorem, and there are very old and nice paper by Azala Faro or Ganguly, where they state and they solve the problem which on some spaces what are the functions of negative type. So there is an analytical way to solve the problem of the existence of the Lévy fractional Brownian motion. It is to be sure that this distance to the power 2h enjoys such a properties. Here I give a definition, and it stands called the fractional exponent of the metric space, not of the process or of the field, but of the space. And it is the largest number such that the fractional Brownian field exists, which can be translated in this property because of the previous slide. One of the problems is it clear that when you have, let's say for H, a Lévy Brownian field, or fractional Brownian field, if you take the lower H, does the fractional field for the smaller h exist also? And the question is solved analytically, and you know that, and we have heard about it in the conference, because actually, if you consider a function which is of negative sign, and you apply a Bernstein function, I do not recall the definition, but we heard about it, then we know that the composition of the Bernstein function and the previous function is still of negative type. So here it is very clear what you have to do. Let's suppose you already know 2h works. You multiply by alpha less than 1, and you know that it works also for alpha h. So basically, you know when it works for he, it works for all the h below. And one of the questions you may ask when you have a metric space is, what is a fractional exponent for your metric space? And what we know, and I will try to recall why, and give you, and think a little bit on the method we use, is that in the case of the vector space, Euclidean vector space, the h here is 1. So let's first try to use spectral theory. So here, what will be on the slide, you know it very well. It was called harmonizable representation by Robert yesterday. The problem here is it is a way that can be generalized to more general manifold to show that the distance to the power 2h is of negative type. And I will start from the formula you know very well. And at some point I will wave my hands and say, this can be generalized. And I will not go into details, but if you want to have details, I refer to Gangoli or Arzada Farley, because it is written. And on one kind of manifold, you can use this spectral theory. If you know a little bit about geometry, I would say that you need a Fourier transform somewhere. And the nice objects, the nice manifold for which you have a Fourier transform is what we call a symmetric space. And I will give you some example of symmetric space later in the talk. Anyway, let's start with the harmonizable representation. We saw that yesterday. Because we have a white noise, we use the isometry property of the white noise. So the variance here is nothing but an integral with respect to the Lebesgue measure. What I will do that is I will use polar coordinates. And you have actually polar coordinates on symmetric spaces. Then, with an elementary computation, you see that the homogeneity you have for this measure is translated to the homogeneity of the radial part of the polar decomposition of the measure. And I state something which is very elementary and clear, the fact that with a change of variable, you have the homogeneity you require to call this a fractional Bonnen field. But here, you have an integral. And it is quite interesting to understand why, in the flat case, h is between 0 and 1. If you want to read it on this formula, it is because you have to take h between 0 and 1 to have convergence of this integral. So here you have a way to have an access to the fractional exponent of your space if you can generalize in some sense the harmonizable representation. I would like to write it in a bit different way. Here I will take y the origin. So it is very simple, it's just the previous formula, that in this case, because it is vanishing at y, then you only have this, which is, by the way, the distance to the origin to the power 2h if you are in a merged general situation. And you have something like this, where I did not phi s, what I got previously, and which is, in this case, this function, which I think is a Jacobi function, is a classical function. Anyway, this kind of function exists in generality on symmetric spaces. They are called spherical functions. And one way to prove, which is not easy by the way, that you have fractional Brownian field on symmetric spaces where you have such a spherical function is you start with, for instance, your distance to the power 2h, and you wonder if it is non-negative. But you have a very strong result called the Lévy formula, but Lévy formula for Gaussian field, which say if it is of negative type, then you have a spectral decomposition of it. And the spectral decomposition goes with an integral part, where S is a spectrum. Here, in our case, the spectrum is 0 plus infinity. It is a spectrum of some Laplacian. And you take a Laplacian which is isotropic. And here, when you know about your symmetric space, you know what is S, and you also know what is the spherical function. So the big deal, and it's not easy at all, is to find what we call the spectral measure. You may wonder what is Q. Q is some quadratic form. I just remind you the flat case. In the flat case, you have the special case when the fractional exponent, the fractional index for the process is 1. Let's think to the one-dimensional case. In this case, you only have a straight line with a random slope. And in this case, the distance to the power 2 is a quadratic form. And this remark is generalized in the Lévy formula, thanks to Gangoli, by the fact that he defined generalized quadratic form. So in some sense, if I want to summarize all I said before is, if you want to use harmonic analysis, you are using Lévy formula, but you need additional structures like symmetric spaces. Let's go to a classical way to consider Lévy fields. Here I'm only interested in Lévy field for the split space and consider another geometrical construction. I will consider, my picture on the whiteboard will be in dimension 2, but the slide is in every dimension. So I consider hyperplane of your space, which are not containing the origin. It is a technical point, you can forget about it, it's not very important. The important thing is, if you take a straight line, which is not going through the origin, if you fix an axis, you have a way to parameterize your straight line with the distance of the origin to your straight line, and with the angle with the reference axis you took. So it is just a way to parameterize the things, and if your dimension is bigger than 2, then you can use, instead of an angle, some unit vectors on the sphere. And then the group of isometry comes into play. What you want to do is to have a measure on all of the straight line of R2, which is actually invariant with the action of isometry. And it is quite classical, and the solution is very well known. Actually, if you think of this as polar coordinate, but not for point, polar coordinate for straight lines, then the measure, which is invariant with the action of every translation, every rotation, symmetry, and so on, the whole orthogonal group, is the angle times the distance to the origin. It is not r to the power d minus 1. It's not the Lebesgue measure, but it works in this case. So, what is the relationship? How can we use that to construct a Lévy Brownian field? It is very well known, and a lot of people in the audience did explain that before. You consider a point M, which is different from the origin. And you associate to this point a set of straight lines. And the straight the set of straight lines you consider is all the lines that will separate the origin from the point. All the lines I draw here are working. This one is not working. And you consider also a white noise, but you consider a white noise on this set with the borers and manifold and with the intensity measure, which is the one which is invariant. And then, if you consider for every point this why not apply to this set, then it's pretty easy to see that you have a Lévy Brownian field. How it works? You take the increment of your field and you use the isometry. Because of the isometry, here you have the characteristic function. And if you think to what we did here, actually you have here the set of hyperplanes that separates the point M and the point N, or the set difference between the two sets here. And what is important and related to the invariance I recalled before is the fact that this measure is related to the distance. And then when you use both relations, there is no problem. You know you have a constructive way to have your Lévy Brownian field on the flat space. With Bernstein function or Ockner subordination, what you know is you can do that for h bigger less than 1/2, because here for Lévy you have h equal to 1/2. It means with this method you don't know that it also exists for h larger than 1/2, between 1/2 and 1. Anyway, you have a passage result. What is nice with this method is the fact that it can be generalized to more general manifold. Go slowly first. Let's take something which is curved, but very similar to the flat space. So I will consider something which a sectional covariance which is constant. In this case, I have two choices, positive or negative, and the negative case is maybe better because in this case we have hyperbolic spaces which are non-compact. We will come back to the compact case, which is the Euclidean sphere later. So let's try to do the same as before. Let's consider a model for the hyperbolic plane, which is the disk model. And what you have to understand is what are the straight lines. And what is very important in the talk after that is you consider the straight line as the geodesics. I mean, here I consider a Riemannian manifold. So I have a way to measure the length of the path. And the straight line are the shortest way from one point to the other point. And geodesics have exactly the same definition. So the question, if you are in dimension 2, it can be also generalized to more two-dimension greater than 2, is what are the straight line on hyperbolic plane? It's quite classical and elementary to see that those lines in the disk model are the circle which are orthogonal to the boundary. But you have also a special case which are the diameter, which do not look as a circle, but at least they are orthogonal. Anyway, you can play the same game as before. You have a set of geodesic. You can wonder, does it exist a measure which is invariant with respect to the isometric group of your space? And I will not give you the parametrization of the measure, but actually it exists and it is quite classical to find. And moreover, when you consider exactly the same question, that is, you take a point M and you consider the set of geodesic that separates the origin and M, and you put the measure, the invariant measure on this set, you have the same relationship as before. So it means we can use the same argument, and even in the case of the hyperbolic plane, we have a Lévy Brownian field for the same reason. So here I said a word when n is bigger than 2. Okay, it works. Let's try to do better. Let's try to go to the Euclidean sphere, which for some of which might be easier in some sense for people not used to work in geometry. So here I will try to do the same, and it is when I say I, obviously it is a classical method, and actually I think it goes back to Paul Lévy, such a method. So it's very old. Anyway, I take M, and here I will draw only a circle, and I consider what I call the antipodal hemisphere. It means I consider the set of points, if here you have the North Pole, which are closer to the South Pole than the North Pole. Then you can use the surface measure or the length measure of the circle if you want. And you still have the same property. It is a representation of your distance with respect to this measure, and you have this set operation of the set you consider. So here I have a slight problem regarding uniqueness. It is the fact that if you consider every random variables you have in your field, they are not vanishing. So one way to have this is to subtract one of them. For instance, the random variable considered for the North Pole. And here again, you can show that you have a Lévy Brownian field. You may think I tell you 3 times the same construction, and it is completely true. Actually, all these constructions can be deduced from a single one, and I refer to a paper by Takeneka, where only one construction is performed on a projective space. Yeah.
So I made them sound. So on all of those spaces, the highest exponent h is 1, right?
Yeah. No.
No.
Sorry. No. We will see that the exponent is 1/2 for the sphere and for the hyperbolic plane. It means exactly, and sorry, it's a very good question. It means in the case of the flat space, this method doesn't give you the full scope of the Earth exponent, but for the hyperbolic plane and the Euclidean sphere, it gives all the exponent you can get. So it is a weakness of the method. And let's see exactly what happens. Here, I was a very positive guy. I wanted to show that it exists, but you ask a very important question. Can we do better than when the method gives naturally? Let's consider the circle case. So the sphere in dimension 1, which is very easy. If you are already bothered, if you think you didn't understand what was previously, you may come back into the talk now, because it is very elementary. I didn't need anything before to explain what it is here. Let's take a circle with a perimeter 2 pi. Then you consider the distance, which is the Riemannian distance here, which is only defined with the angle, and which is this one. It means when you have 2 points, on your circle, if this distance is shorter than this one, you take this one. If it is not the case, you take the smaller one. And then I will try to check positivity. So I take a special configuration. Sorry, I don't need that yet. I take theta between 0 and pi, which is not very important. I take 1 point, P1, for instance, the North Pole. And I take P3, which is the South Pole, or the antipodal point. So here I have P1, here I have P3. and I take another point, P2, and you may take whatever angle you want. But P4 is the antimodal point for P2. And then you consider also weight, and you want the sum of the C, which is vanishing, just to check the non-negative property. So you take -1, 1, -1, 1. I said it once too much. So here you have the configuration, and you do the computation. You do the computation, but here you have a formula for the distance. If you compute the variance of this linear accommodation with 4 terms, then using the covariance I stated before, you don't need all the case, and you only have this one. It is because we have the Lévy Brownian field, so 2h is equal to 1. And what you see is, using this formula, that it is vanishing. So I recall that it is for every theta. You have a very special construction here. And you see that the Lévy Brownian field on the circle is degenerate, which is obviously not the case on the real line. And we call this kind of configuration, here you have just an example, critical. Coming back to your question, Gennady. Actually, if you want to show that you cannot have an Earth exponent strictly bigger than 1/2 for the circle, you may use Lévy-Kitchin formula. Lévy-Kitchin formula is said spectral so on. It boils down in the case of the circle on a series Fourier's expansion of your distance of this function of theta. It is nothing but a series Fourier expansion. So it means if I consider the spectral measure, it is a weighted sum on the Dirac masses which are on integers for the circle. And the problem boils down to the fact that these weights are positive. And you can find in the paper by Istas that when h is bigger than 1/2, then it is not the case. They are not positive. So we are not using the same tool, but we can show it's not good for h bigger than 1/2. Okay. And here, let's think of what happened in higher dimension. And this thing is pretty important. Let's suppose you have a sphere in 2 dimensions. Everyone who will take the plane knows that the geodesics are the great circle on Earth, on the sphere. So the great circle, there are just like S1, but they have an additional property. You have a submanifold of your big manifold. But if you take any 2 points in the submanifold, then if you consider the geodesics in the biggest one, in the largest manifold, it stays on the manifold. And in this case, if you have fractional fields on the biggest manifold, you should have fractional Brownian field on the submanifold. So it means the obstruction you have for S1 is also an obstruction for Sn bigger than 2. So now I'm using what Neil Venet introduced quite recently. It is a way to start from the circle configuration and to show that you have obstruction result for your manifold. So we start with a critical configuration, and I introduced you to one configuration before. And the idea in Neil's works is to consider a perturbation of this. So you will consider a point quite close to the configuration. You don't change the weight usually, and you will see, because this one is 0, and because you use curvature to make asymptotic expansion, that you can choose the geometry such that this one is positive, and then you get an obstruction. Let's see the result, not only the method. I should say that before Neil Venet, there are old and beautiful results by Morozova and Shensov where they knew they have obstruction. other kind of obstruction. I have no time to explain the difference, except if you ask me for a question. But it's not, Lévy is not the first one to get obstruction starting from the circle. Anyway, in Lévy result, you have to consider some tangent space. So it is a general fact. You have a point P1 on a manifold, and you consider a point close to this point. There is, in full generality, if P2 is close enough to P1, a single geodesic that starts from P1 and the end is P2. So it has a single speed vector at the origin. So if we denote, if we suppose here we have P1 and here you have only one J different from P1, then this space actually is just dimension 1 if P1 is close to P2. But if you think to what happened for the sphere in dimension 2, you take the north pole for P1 and you take the south pole for P2. Then all the great circle, all the meridian of your sphere will be geodesics going from P1 to P2. So in this case, you are in a very classical situation in geometry with cut locus, where actually the dimension of this space is 2. It is the dimension of the surface where you consider the configuration. With these two, we can see obstruction for the existence of the fractional Brownian field of the Lévy Brownian field. Let's start with the case H is 1/2 on manifold. Let's read together this result. We start with Riemannian manifold. Complete means for every 2 points you have a single geodesic that goes from 1 to 0. And let's suppose the fractional Brownian field exists. Then, every time you have a critical configuration, you should have the dimension of the space I explained you before, where here you consider geodesic coming, if you think to I equal to 1, you consider all the geodesic coming from the other point. And you consider the space generated by all the vector, the speed vector. And with the results from Venet, you see that if the Brownian field exists, then you have this geometrical assumption. Maybe it's not quite clear for you, but it is not many manifolds enjoy this property. Let's see a little bit more what we can do with these two. First of all, we need a critical configuration. And what I know is I have critical configuration on the circle. So I will search for a circle in my manifold. And what is a circle on a manifold? It is a geodesic, but a geodesic like this, or the case of the sphere in dimension 2, which is closed. And moreover, you want that the distance in your manifold between any 2 points on your geodesic is actually achieved through the length of the geodesics between the 2 points, either this side or this side. It is what is called minimizing geodesic. And here I consider manifold where I have some S1 embedded in the manifold. So I know at this point that there doesn't exist any Lévy fraction, any fractional Brownian field with h bigger than 1/2. But the question is, does it exist for h equal to 1/2? You can work a little bit from the theorem, and you see that on your geodesics, if you take 1 point, and the antipodal point P star. And you still consider this space, TP P star. Then, if there exists a Lévy Brownian field, the dimension of this space should be the dimension of the manifold. Hopefully, it is true for the sphere in dimension 2, because we know the Lévy Brownian field exists. But actually, the case of the sphere in dimension 2 among surfaces, I mean Riemannian manifold with dimension 2 is very special indeed. We have another result, which is quite strong, I think. Let us consider the case just as the sphere in dimension 2 of compact manifold. If you have some information on the topology, and only on the topology, you suppose that your manifold is not simply connected. It means you have somewhere a loop which is not homotopic to the constants loop. Then, with this corollary, you can show that there exists no Lévy Brownian field indexed by the manifold. And you have a lot of examples for that. I just set one here. You can take the ORIE. What is very important in this result is here I have a topological obstruction. But for instance, on the ORIE, I can define more than one metric. I can define the flat metric. But I can also consider the ORIE embedded in the usual space, the tire, if you want, in the usual space. It doesn't matter. Because here you have only a topological obstruction, you see that there doesn't exist a Lévy Brownian field. Okay, in another paper, Lévy considers the case of the cylinder. First of all, I should say what happened for the Lévy Brownian field on the cylinder. And it was actually the starting point of the PhD thesis. And actually, in the beginning, it was one question raised by Istas a long time ago. And he said, well, we know the Lévy Brownian field on R, we know the Lévy Brownian field on the circle. Can you give me a construction for the Lévy Brownian field on the circle times the real line with the product matrix? I started to work a bit during the conference, shame on me, and to try to construct the things. Then Lévy came to me and I asked him the question because I was not able to solve the problem. And what we discovered with some variation of the previous result is the fact that there is no Lévy Brownian field on the circle. So then the question becomes, okay, we know that the fractional exponent for the cylinder is less than 1/2. But what is this fractional exponent? And we were quite surprised to show that actually the fractional exponent for the cylinder is 0. It means there exist no fractional fields on such a simple object as R times S1, which is a Lévy Brownian field. It is not the first example of a metric space such that the fractional exponent is 0. One is given in Ista's paper, and you take a non-Riemannian metric on a very nice space, which is the vector space in dimension 1, but here you take the LQ distance with Q bigger than 2, and you can show there is no fractional Lévy field on this field. So I would like to make some comments on the references. Here you have the old but very nice paper related to the Lévy-Kenshin formula. Here we studied with Michel Lifshitz very much the case of hyperbolic spaces, and we tried to compute, after Bolchan, the spectral measure related to the Lévy Brownian field on and the fractional Brownian field, the Lévy Brownian field on the hyperbolic plane. This paper is introduced some tools you need in representation theory for group, and here you have the results, where here obviously to be fractional in the right order, where they show that for h bigger than 1/2 you don't have any fractional Brownian motion on the circle. Istas showed that. Here is a review by Istas that I used in the beginning. Here it is a very nice and short, as usual, with Russian at this time, paper by Chentsov and Morozova. Here you see the construction on the projective space, and then you have the two references by Nilvene, which are quite recent. Thank you very much.
Well, thank you very much, Serge, for this exciting presentation of difficulties of the industry manifolds. Any questions, comments?
Other functions that might be good to measure distance between those two random variables, other than the natural distance. What do you think about that? Because it's geometrical and this is an obstacle. Something like green functions.
Oh yeah. The answer is yes, even in the literature. For instance, I didn't put other attempts to have generalization of Lévy or fractional Brownian field on manifold. One is quite interesting, and by Gelbaum. It's not exactly an empirical equation, but it shows that here it just presented some result, not all result. And he started from the harmonizable representation. And he said, well, you know, the kernel is some solution of some partial differential equation related to that action. So let's consider an harmonizable representation and use the solution which is defined in general. And then you get something which is Lévy fractional Brownian motion in the flat space, and which may exist in other cases. But it is not, it has not the exact distance for the variance of the increments you have on the platform. I was very excited when I read the paper. I was very disappointed when I saw that on the cylinder it doesn't exist. In some sense, there are many attempts quite exciting, but no one is really perfect.
Any others? Yes.
So it's a general question. So do you think it's interesting to think of the discrete model to approximate your structure on manifolds? I believe that you can do it in some, say, routine or artificial way, but are there kind of interesting discrete models will lead to this stuff that you study here?
No, I don't know how to do that. I mean, you can define a Lévy Brownian field on a graph with a Hamming distance or any distance.
Graph, the approximate manifold.
Yeah. And one of the questions is, does it exist a Lévy Brownian field for such a graph? And at some point in the PhD study, during the PhD thesis, I asked Neil to do simulation. So he takes random points and he fixes distance. He has to check that the triangular inequality, but you have a random metric space which is finite. And you wonder what is the fractional exponent for this space. So it seems very simple. But the results of simulation are puzzling me. I have nothing intelligent to say on that. On the other side, if you start even from the chance of representation of the Brownian Lévy field on the plane, there are various discretizations that you can take, but I would like to have one which is goodly, well behaved. with respect to the isometric group. And then if you want some invariance with respect to the isometric group, I don't know one which I like. I mean, they are, but it is in contrast with what happened for the Brownian sheet where discretization is obvious.
Any other question? Well, I should have several, you know. So for example, in some nice paper.
I stay this afternoon, you may.
That's right. Yeah, so like in the Hilbert space, anything nice happens?
It's the second time you ask a question of the Hilbert space during this conference.
Okay. Okay.
And actually, I will repeat what I told you privately.
Okay.
There is also a paper by Istas where he considers multifractional Brownian process. There is no geometry in the paper, but indexed by an Hilbert space. And so, go back to ISAIN-PS, which is a review where the paper is. It's not one which is quoted here. And you will see that it works, but it is only finite-dimensional distribution of the process are defined. So going to a set of parameters which is infinite, you have other troubles, which are quite classical for Gaussian field.
So one can consider a slight generalization, still you have a distance, nice distance function. Well, you presented this very nice presentation of what powers of this distance function are negative definite. The powers are a special example of their correspond to subordinators in finite dimensions. So maybe more generally one could ask, if you take a function phi, distance, what phi is equivalently subordinate. So is there anything wrong with that?
I completely agree. If you go back to the reference with Michel, you see that the chance of construction for the sphere, you can try to mimic it for the hyperbolic plane. But there is a problem. We already use it for the hyperbolic plane. And we use set of geodesics. So we tried something else. We tried orocycles. Actually, the chance of construction is very, you can change it a lot. You just need a set on which the isometric group is operating. And the relationship with what you said is, we get the process, and in the beginning we thought we add the Lévy Brownian field and so on, even if we have another construction to that. Okay? It doesn't work. We have something related to Einstein-Uhlenbeck processes when you take the oral cycles. So, if you are not interested in the spatial power, 2h power of the distance, we know things. Actually, we can work around the Lévy-Brownian formula and have constructions which I think are quite interesting. But I recall that the name of the conference is Self-Similarity. So basically, I would like to know something on fractional power because I feel like fractional power is linked to self-similarity.
Okay, I'll ask one more question and we'll let you go. So, I hope so. So, are there any, you mentioned that issue this critical exponent can be in some cases even bigger than 1, right?
Yeah.
So what are the examples of this one?
I cannot recall the result. I think if you take 4 points, metric space with 4 points on a square, you have a nice example in Istas paper where you fix the diagonal, the length of the diagonal, such that triangular inequality is true, and then you vary. You can even have infinity actually for the fractional exponent.
Okay, unless there are any other questions which I want to, let's thank Serge once again.